Now when we got some inference about how these confidence intervals and uncertainties work for proportion, let's do some calculations. We will use the parametric approach for calculating confidence intervals, meaning that first of all we need to know which distribution the sampling parameters, the sampling statistics follow, which distribution. And then as soon as we know that, we calculate the parameters of this distribution. And then we use the parameters for calculating intervals. Okay, so that's the parametric approach for the inference, for calculating confidence intervals. So let's start with splitting this in two cases. So with population, what about population? Population and sample. Okay, sample. So we have like two cases here. Well, and then we have some general things here. Well, when we talk about population, there are different ways to denote proportion for population. In some cases, they use capital P. In some cases, they use this Greek letter pi. Okay, we will use Greek letter pi in this case. When we talk about sample proportion, in most of the books, they use this small p with a little hat on top of it. That means estimated value when you have this little hat on it. So we'll use also this notation, the small p with a little hat on top. Okay, so we know that there is a population proportion. So population proportion is actually just a very simple thing. Okay, it's a ratio between x and n, where x, it's a number of values from a certain group. For example, number of red balls, number of males, number of people who smoke, and so on. And n is a population size. N is a population size. So for example, if you have 1,000 people and 300 of them smoke and 700 do not smoke, it means that the proportion of population is 0.3. Okay. Now, similarly, the sample proportion can be defined as a small x to small n, where they have the same meaning. Small x, it's a number of values from a certain group in your sample, and small n, it's a sample size. It's a sample size. The problem is every time we take a new sample of the same size, the proportion for the sample will vary around the true population proportion somehow. And we would like to know how far it can go from the true value, learn how to calculate this uncertainty, all that kind of thing. Let's start with some general things. First of all, the sampling distribution for proportion, sampling distribution for proportion. So it means that if we take many samples and look how this values, the proportion for the samples from the same population are distributed, is normal. So that's a good thing because we know almost everything about normal distribution, right? We know that normal means we should have two parameters, the average and the standard deviation. So the average for these proportions, it's actually the proportion for the population. So it means that if we take many samples, calculate proportion for these samples, the average will be the proportion for the population, what we are looking for, right? And then the sigma, the standard deviation, is the following. It's a square root of the true population proportion, then 1 minus this proportion, and divided to the sample size. Okay, so let's think about this sigma. So p, we know pi, it's a true proportion. What is 1 minus pi? Well, if you think about, for example, two groups only, like males and females, if pi gives you the proportion for males, then 1 minus pi, it gives you the proportion of not males, in this case females. Okay. And then look, we have this n in the denominator, which means if the larger sample is, the smaller sigma will be, the smaller spread, the smaller uncertainty for this proportion deviation will be. So if you want to be more certain, if you want to get more precise results, just take a bigger sample. Okay. But we know that this works only if we know the population proportion. What if we don't know? Well, if we don't know the population proportion, then we can replace it with a sample proportion, with estimated proportion, but with a certain requirement. So we can say that the mu is the proportion of a sample, and sigma It's the same way, we calculated the same way, but using the proportion of the sample. Okay, divided to n. Okay, but only if n times the proportion of the sample is equal or larger than 10, and n times 1 minus proportion of the sample is equal or larger than 10. So what these two values mean? It means that you need to have at least 10 members of the group and at least 10 non-members of the group. So that's why, if you remember, then we deal with this small shiny application. When sample size was small, like we did 6 and 10, it didn't work well. But when sample size was 20, it worked very well, and actually the uncertainty was even smaller than expected. So that's why, let's say you have n equal to 20. If n equal to 20, you need at least 10 values from the group and at least 10 values not from the group. Okay, so it means that n equal to 20 will work well for proportion 0.5. But for example, if you have proportion 0.3, then if you take 20 times 0.3, it's 6. So it's less than 10, so it will not work. You need a bigger sample size. Okay. So once again, we can use normal distribution and parameters estimated from a sample, but only if sample size is large enough. Only if sample size is large enough. Now let me show you some calculations for these two cases. When we know population proportion and when we don't know the population proportion. So let's start with when we know population proportion. Let's use this smoking example. Let's say we have a population, all students in our department, and we know that for the whole population, the amount of students who smoke is equal to 0.2. So 20% of students smoke. So what it means? It means that if we take a sample size, if we take a random sample, and let's say the sample size will be 50. So if we ask 50 random students out of 500, so let's say the n, the bigger n, let's say it's 500, okay? So it's all students in our department. Actually, we have a little bit more. So if we take 50 and the proportion is 0.2, then the confidence interval can be calculated as follows. First of all, we know that the mu will be 0.2, okay? And the sigma, so how far this proportion of sample can go from the proportion of the population, is calculated like this. So we have 0.2 here times 0.8 here and divided to 50. If I do these calculations, it will give me a 0.06, approximately 0.06. Okay. Now what this means? It means that, for example, if I take a random sample from this population and sample size will be 50, then in 68.3% cases, because it's normally distributed, the proportion for my sample will be within 0.2 plus minus this 0.06. Okay. So in 68% cases, the proportion of my sample, it will be random value. I can never predict which it will be equal to, but I know that in 68% sample cases, it will be somewhere here. Okay. With 95.5% cases, we know that for normal distribution, we should take two standard deviations. So it will be 0.2 plus minus 0.12. Okay. So it means that if I take a random sample from this population, the proportion for the sample can be, in 95.5% cases, can be somewhere between 0.08 and 0.32. Okay, so it can be 0.1, it can be 0.3, it can be 0.25. So it always will be around the 0.2, but it will be a random number. So we can never predict this. So this gives you an uncertainty, how sample size influences the uncertainty for the proportion of your sample. Okay. Now let me show you how to do these calculations if you have no idea what's going on with your proportion. Okay, so imagine that you took a sample and the sample size was 50, and the proportion for your sample, was 0.2 again. Let's use the same. Okay, what it means? We don't know what the population proportion in this case. Well, first of all, we have to check if the sample is big enough, right? So first we check if n times p hat is above or equal to 10. So we have 50 times 0.2, which is actually 10. And we know that we are exactly on the border. So we have at least 10. That's enough. And then we do the same for n1 minus p hat, which is 50 times 0.8, and it gives us 40. So we have 10 students out of the 50 told us that they smoke, and 40 told us that they do not smoke. Okay, and these are good requirements. So we have a big enough sample. Okay, now the average in this case, we estimate the average as the proportion itself. So it will be 0.2, and the standard deviation. In this case, it will be the same. I just took the same numbers to make the calculations easier, right? So it will be, so it's 0.2 times 0.8 and divided to 250, which gives us the same value, 0.06. But once again, in this case, we use statistics of sample. We have no idea about proportion of the population. Okay. Now we know that if we take 95.5% cases, because the proportion is normally distributed, so it will be 0.2 plus minus 1.2, right? 1.2. So it means that in 95% cases, the true population proportion is somewhere between these two values and 0.32. We don't know exactly where. It's somewhere between 8% and 32%. Okay, and we can't make it more precise with this sample size. So that's what we have. Then you can use the same calculations for any proportion. For example, if you would like to know what kind of countries people prefer to travel to, or would like to know which color of clothing people prefer, so you can take a random sample, ask people what do they prefer, calculate proportion for every level, and then use this calculations for computing what it will be for the whole population. So if you ask not 50 people, but maybe 5 million people.